Hi everyone, I'm Hanning from Carnegie Mellon. Today I will be presenting our work towards principal disentanglement for domain generalization. Domain generalization concerns generalization beyond IID data, which is common in realistic applications. The tasks on the slide here are just examples of a long list that grows by the day. In the past few years, we have seen remarkable progress in improving and creating new models for various such tasks. However, generalizing to unseen domains is still considered difficult. Data augmentation is shown to be effective in various domains, but it heavily relies on human bias about the variation factors. On the other hand, domain-aware training is popular and scalable, but unstable and require domain labels, which are expensive in the real world. Another motivation of our work comes from the intricate connections between disentangled representations and domain generalization. One reason was shows that generalization was limited and suggests that models are simply generalizing on the basis of overall similarity, namely interpolation, rather than exploiting disentangled representations in order to support a more powerful form of compositional generalization. A third motivation of our work comes from the observation that many related work didn't employ a unified evaluation protocol, which makes a pathology that many well-known methods even underperform ERM. Based on the above discussions, we are seeking a method that can explain the effects of disentanglement on the domain generalization, supports stable and effective training under a unified evaluation protocol. Moving forward towards this direction, we propose a principal disentanglement framework for domain generalization. Next, we will show how we can formulate the domain generalization based on disentanglement for a wide variety of domain generalization tasks. The first definition comes from the invariance based on disentanglement effects. Intuitively, we split the representations into two independent semantic and variation spaces, such that reconstructed inputs keep their similarities to the semantic inputs regardless of the variation ones. We also adopt a minimax by-level optimization framework. But the worst group formulation is notoriously hard to optimize, and given the parameterized decoder, it is not easy to analyze either. To resolve the above challenge, we resort to an inequality-constrained domain generalization problem, which is a relaxed version. However, the problem is infinite-dimensional parameterized and still needs finite-dimensional parameterization to solve. Thus, we use two encoders to parameterize the semantic and variation representation separately, which leverages the definition for to arrive at the epsilon star, as the definition is over the ground truth data distribution, which is not available in practice. We leverage empirical samples to approximate the population estimate. Through the above transformations, we finally arrive at a dual problem, the epsilon n star. This problem is much more checkable since it is a regularized ERM without adversarial training. It also enables algorithm and framework design since we can leverage neural networks for parameterization. It is also easy to analyze since it can be used with classic pack learning bound, which we will show later. Next, we will show how we can develop theory and algorithm based on the above formulation. With the formulation in the last section, we can design our model by parameterizing a variational encoder, a semantic encoder, and a decoder or generator. We call the method DDG for short. The goal of DDG is employing strong regularization for minimizing domain divergence and promoting semantic invariance. As shown that given 4 input digits with different rotating angles, ideally the representations are well disentangled, we can generate 4 additional digits for training. In this way, DDG automatically enforces robustness to different variation factors. Moreover, it provides a natural data augmentation technique which is domain agnostic. To train the DDG framework, we need an efficient optimization technique. We resort to a primordial algorithm which iterates between the model and balancing parameter update. We made the decoder trainable as well, which allows flexible training, such as improving the generation quality using a cycle gain objective. To analyze the above framework, we derive an empirical duality gate which bounds the final version of the transform problem to the original one. We call that one of our objective is to explain why disentanglement can help generalization in certain ways. In this work, given our analysis, we can see that the generalization bound is strongly related to the strength of disentanglement since the gap is governed by epsilon s and epsilon g, which means when reconstructed inputs are visible to the semantic inputs, the generalization can be improved. Next we will show how DDG works for a wide variety of domain generalization tasks. We first showcase the quantitative results of DDG compared with popular approaches. We can see that DDG is consistently the top performer over 4 datasets in almost all the domains. What's noteworthy is that the performance gap and worst domain generalization of DDG is larger in datasets like PAX and VLCS. It makes empirical sense since those data are variation rich, which means DDG can better harness variation factors to improve domain generalization. DDG gives smooth convergence curve, which is similar to ERM. This is in stark contrast to domain adversarial methods like DAM and CDAM that tend to be diverged as training goes on. What's more, DDG learns invariant features that are measured by the DA distance compared to baselines like IRM and ERM. DDG also serves as an alternative data augmentation that are effective across domains impacts compared to traditional methods like omics. Now we're going to showcase some qualitative results on the effects of disentanglement. We use the cycle gain for improving image generation quality. We can see that we can swap variation codes of 2 inputs for diverse image generation. What's even more interesting is that DDG allows more fine-grained control of various kinds of variations. Recall that rotating m-ness has a rotation angle as its dominant variation factor, but DDG can disentangle both rotation angle and the thickness of digits. Moreover, the examples in data with richer semantics show that DDG is able to recognize semantic information since the color of the dog's eyes and nose remain unchanged during reconstruction. Similar phenomena are observed in the camera medical data. To conclude, we have proposed a simple yet effective framework for domain generalization. DDG flexibly harnesses the semantics and variation factors to minimize the semantic difference of the generated samples from the same class, while diversifying the variation such that it enables a wide variety of goals, including domain generalization, disentanglement, and controllable generation. We analyze the tight connections between disentanglement and generalization under pack-constrained learning framework. We use a unified evaluation of all datasets for fair and large-scale comparisons, and empirically show that DDG outperforms previous methods. Furthermore, the framework opens up exciting possibilities for studying the inner connections among disentanglement, domain generalization, and controllable generation. We are excited to explore more in the future. Thanks for listening. To learn more, feel free to check out paper and code by scanning the QR codes here.